Okay, so we're going to look at the last part of this chapter, which is going to be using mass percent, looking at percent composition, and also looking at something called empirical and molecular formula. So just to review a percent in general, any percent is going to be some kind of part over a whole times 100. So a percent is a fraction, and then we multiply by 100 to get a number that we use to kind of decide how much something is. So you're probably very familiar with percentages. If you've ever gotten something on sale, 20% off or something, you're probably very comfortable with that. So take that level of prior knowledge, understanding about what a percent is, and we're just going to apply it now to compounds and elements inside of that compound. So mass percent composition is going to be, if you're looking for a mass percent of a certain element, let's just call it X, that's inside of a compound, it'll be the mass of the part, the element you're looking for, over the whole or total mass of the sample times 100. So very kind of simply, not really, doing too much beyond part over whole. It's just identifying what is my part here. And in this case, we're talking about percent composition of a compound. The part is going to be the element that you're looking for and how much mass of that element is inside of your compound, and the whole is the whole total compound here. You will do this in your percent composition lab with experimental numbers. You'll also do it with molar masses or formula masses, which are the theoretical numbers. So let's look at an example here. So in this example, and you can pause and try to work it out if you want to, but it's very straightforward, so I'm not going to try to spend a lot of time on how to do percent math. But if I have 0.358 grams of chromium, okay, and I react it with oxygen to form 0.523 grams of a chromium oxide. Chromium is a type 2 metal, so I don't really know how many chromiums and oxygens there are. I don't really know the charge of chromium, so I'm just going to say, hey, some metal oxide or some chromium oxide. If I'm looking for the mass percent, it's going to be my part, which is just the element I'm looking for. So mass percent of chromium, see how the element chromium for the mass percent is the same as the part of the compound, over the mass of the total metal oxide. So what we've done here is we've taken the mass of the chromium that we know is reacting when we're assuming all of it reacts, and that's going to be our part. And then how much total chromium something oxide we make is going to be our whole, and we're going to multiply by 100 and get this answer. I would not use the percent key in your calculator, but just use 100. And the percentage is just a unit showing you that, hey, this is a percent, it was multiplied by 100. To get it back to a fraction form, you would have to divide by 100. So let's do a little practice with a percent, and we can use a percent also as a conversion. So in this question, I'm asking you for the percent. So kind of like when I ask you for density, you got to plug in the mass, the volume. But if I'm giving you a percent, like I am here, with this question, you can actually use it as a conversion factor. So I encourage you to pause and try to work through this problem. I'm giving you a hint here of how to write that conversion factor, but we're going to look at it together. Okay, so a couple of things that I want to note when I'm reading through this problem. The FDA recommends adults consume less than 2.4 grams of sodium per day. So that is a conversion factor, and I can kind of write that. So if I'm thinking about what am I given, okay, how many grams of sodium chloride can you consume and still be within the FDA guidelines? So I'm assuming that I'm asking about how many grams in a day. So I'm going to throw out here that perhaps my given is 1 day. How many grams can I consume? And I'm going to assume here in 1 day. Since they give me this per day, they don't really tell me, like, in my lifetime, in a week. So we're just going to assume, like, hey, like, how much sodium chloride can I eat in a day? My unknown And that's kind of hard to tell the day. You don't have to do the 1 day. You can do it without that. You could just say 2.4 grams of sodium. Since it is per 1 day, that can be your given. So we could say, or 2.4 grams of sodium. We're going to use our chemical symbols here. And we can just kind of forget about the day, right? Because it's going to automatically cancel. And if you get very good with dimensional analysis, you can do a little bit of that, what I call maybe cheating, and kind of identify some things that may help you go a little faster in your problem. So the unknown is how many grams of sodium chloride. So here you can see that if you don't know the nomenclature very well, if you're not sure how many sodiums and how many chlorines are in sodium chloride, you're going to wind up having a problem when you are doing some of these calculations, because I'm going to give you word problems like this and you're going to have to turn it into formulas. So if you're still kind of working through nomenclature, I strongly suggest you do not give up the practice on that and that you work on it a little bit every week. So then they give me a conversion. So I can use, I can say 2.4 grams of sodium equals 1 day. Totally use that. They also tell me this percentage. So the percentage is a conversion factor. So what I want you to do when you're given a percentage and you think you're going to use it, you can absolutely use it as a conversion, or we can use it algebraically. You know which way I like. As a conversion, we're just going to assume something that makes my percent work out really well. Assume 100 unit of the whole. So we're just going to throw in the unit here. Because they say mass, we're going to say grams. So if we assume 100 grams of the whole, what is the whole here? The whole is the sodium chloride, the total compound. So 100 grams of sodium chloride. Now, how many grams of sodium would that be? It's going to be some number of grams of sodium. Well, if we have 100, what's 39% of 100? 39% of 100 is 39. So that's why I'm assuming 100 of my whole, is because now I'm just taking the number. So the number of the percent can be transformed into the number of whatever unit you're looking at of your part equals 100 of whatever unit of your whole. So that's how we can convert any percent into a conversion factor and then use it from there. Okay, so whatever this number is here is this number. It's the same thing. And the unit is the same on both sides. So just make sure the unit is the same on both sides. But it doesn't matter what unit you use if you're not told. You can pick whatever unit works. They're telling us a mass here, so we're going to use grams. And we can use kilograms, tons, whatever, but they're giving us grams in the beginning here, so we're going to use grams. So how can I write this as a conversion? I can say, well, 100 grams of sodium chloride is equal to 39 grams of sodium. Notice that I can't just write 100 grams equals 39 grams. I have to now include the sodium chloride and the sodium because my units are the same, so something has to be different. It's going to be my substance. And algebraically, which is not my preferred way of doing it, so you won't see me doing this very much, you could say 39 over x, because I'm looking for how much sodium chloride, I'm looking for how much sodium. So it'll be 2.4 grams of sodium over how much sodium chloride times 100 is equal to 39%. And a lot of students have trouble solving for x on the bottom of a fraction. You got to remember to, we're going to divide both sides by 100 first. So we get 2.4 over x is equal to 0.39. Multiply both sides by x to get x on top. And then we will divide both sides by 0.39. So you can do this algebraically. I don't recommend it, but it can be done. I think if you can do more things with dimensional analysis, you will understand it better and you'll also be able to solve more complicated problems. So let's put this into our work. If you start with 1 day, which is totally fine if you skip this part, you'll see that you'll get the same answer. For every day, we can consume 2.4 grams of sodium. And then 39 grams of sodium gives us 100 grams of sodium chloride because I can manipulate my percentage in that way. Canceling out, grams of sodium cancels grams of sodium, not just to one unit and one substance, canceling here. And you'll find that if you did the algebra correctly, you will get the same answer. But to me, it's just easier to see and not second guess myself when I do it this way. So rounding for sig figs, I'm going to get 6.2 grams of sodium chloride as my answer. And I hope that that is what you got and that you're feeling comfortable with dimensional analysis enough to where you gravitate towards that. So like, I don't know about you, but when I'm doing this kind of work, this algebraic work, unless you're like super confident in your math skills, you might second guess your answer. But here I can very clearly see what I've done, and I can see that, you know, yes, these things are true, and then I'm canceling things out. These numbers go with these units, and I feel more confident about my answer, which is going to save me time in the long run because I'm not going to second guess myself and go back to the beginning of the question and scratch everything out and start over. So here's kind of, what if I asked you for mass percent of chlorine, it's like what would be the mass percent of chlorine in CCl2F2? This is a chlorofluorocarbon, it's a pollutant. So how would I do that? So if I don't give you numbers, you can use the molar masses. So because there are 2 chlorines in CCl2F2, I'm just going to say 2 chlorines times whatever the molar mass of chlorine is, divided by the total molar mass of this. Right, so you can just use no given information, use molar masses to find percent composition. This is what you'll do in your lab when you're asked to find the theoretical percent composition. If you're not in a lab, you don't have numbers to find an experimental, you also want to compare it to what should it be, we will use the molar masses for that. So here's a practice, and it's not the same compound we just showed, but it is another chlorofluorocarbon, Freon 114. So go ahead and pause and see if you can work this out. I am giving you a hint here. So we're looking at the mass percent of the chlorine here. All it's going to be is the 4 times the molar mass of chlorine, which we're getting that from the 4 here, over the total molar mass of this whole thing. So just so if you're looking to check your work, we're going to do 4 times 75, oops, not 75, 35.45. That is the molar mass of chlorine. My grams are going to cancel, so it doesn't really matter what my units are, they're going to cancel. Let me just grab another page here so that we are not struggling with this. Okay. Over the total molar mass of C2Cl4F2. And I'm just going to put this all in my calculator. You will get very good at calculating molar masses, but feel free to write it out as you begin to learn this. If you want to see that written out, how I got this number, please text me right now and ask me how I got that number, and I can show you. So we're going to do 4 times 35.45 all over 203.84 times 100, and we're going to get 69.5. For sig figs here, we kind of have unlimited sig figs, so it's a good practice to use 2 digits after the decimal if you're not sure, because we are using these infinite sig fig numbers, these molar masses. So that's the percentage of chlorine in Freon 114. 114 is just telling you the mass of the Freon. It's an identifier. There are multiple Freons out there. Oh, it's not the mass of this Freon, it's just an identifier. Okay. So let's ramp it up a notch and try this challenge problem where I'm going to ask you for the mass percent and then I want you to use that information. So I will grab myself another page here and I'm hoping that you will pause at this point and try to work this out. So to work this out, first I want to have the percent composition, and in this practice I'm actually not challenging you quite as much as I could because I am giving you the formula. I usually will just give you sodium fluoride and will not give you NaF. You'll have to know how to do that. So first, let's section this A and B. First, let's find the mass percent. And because I'm not given any information for that section, I'm going to use the molar masses. So we're going to use molar masses here because they don't really give us any information about any sort of experimental information. So mass percent of fluoride in sodium fluoride. So make sure that you're not saying mass percent of fluorine because F- is called fluoride. So let's set up our formula. Mass percent of fluoride is going to be the grams, and I know I'm using grams because I say mass. So if I say volume percent, I'd use milliliters or something, but the grams of fluoride over the grams of sodium fluoride. How many fluorides are there? There's one fluoride, so I don't need to multiply it by anything. We're going to multiply it by 100 to get that percent. So when we're doing this, we're going to have the mass of the fluoride is the same as the mass of one atom of fluorine. But if I say fluorine, I would be talking about diatomic F2, so the mass would be a little bit different. We're talking here about just one ion, which has the same mass as an atom because the electrons do not calculate into that mass. So you're going to have 19 or 18.99 if that's what your periodic table is telling you. I just have it memorized as 19. And then 19 plus 22.99 is 41.99 times 100. It's going to give us a mass percent of 45.25% fluoride. And I'm just doing 2 digits after the decimal here to be safe. Okay, so that's the answer to this first part, 45.25% fluoride. If you've got any questions, please text me. Now, I can do this section B. If you're a little more advanced or you've taken chemistry before and you're looking at this and you're like, well, I just want to use molar masses, you know, to do like a mole ratio, sure, you can do that. If you want to do a mole ratio, you absolutely can. You can also use the percentage. So I will show you how to use the percentage, but if you want me to look at your work on how to use the mole ratio here, you can absolutely do that too. So how many grams? So let's say let's get some information down. Now I've got a more of a kind of problem. So I'm given 1,500 liters of water. This other thing I'm given is not a given. It's not a starting place. It is a conversion. So let's not put that there. You want to try to only put one unit in your given or starting place spot. So unknown is going to be how many grams of sodium fluoride. This is what they do with us. They put fluoride in our water so that we will ingest that. It is supposed to be good for your teeth, but they found recently that it's not really good. It's not really that beneficial to ingest it as it is to actually paint it onto your teeth. But we still do it anyway. So we need more conversions. Yes, sorry. Thinking about going to the dentist and that derailed me. Conversions, we've got 1.0 milligrams of fluoride equals 1 liter of what? 1 liter of water. So that's a conversion that they're giving us. And then we also have another conversion. We have this percentage we just found. So how can I write that as a conversion? I can say this many grams of fluoride is equal to 100 grams of sodium fluoride. You can also use this 19 grams, 41.99 grams, same thing. But if you want to use the percentage and really practice using a percentage as a conversion, here goes that conversion. So do I need anything else? I have liters of water. Liters of water take me to milligrams of fluoride, but I need to connect milligrams and grams. So I'm going to add another conversion factor. 1 milligram is 10 to the negative 3 grams, or you can say 1,000 millis is 1 gram. That's fine. We'll just make that for fluoride, just to be very careful that we're not, because we are changing substances here, we have to be careful about what we're talking about. And then grams of fluoride take me to grams of sodium fluoride. So I have all the conversions here that I need. And I'll set this up. And again, if you are confused about why I'm doing something, please text me. Just screenshot exactly what you're confused about from this video and text it to me. And I can help you figure out what I'm talking about and get you set up for success. So I'm just going to use my trusty dimensional analysis as much as I possibly can to really reinforce that skill that is a very important learning objective for this class. It's going to help you so much when you move into higher level chemistry. So 1500 times 1, okay, times 10 to the negative 3, which is the same as dividing by 1,000, times 100 divided by 45.25. Looks like we need only a tiny little 3.32 sig figs for that 1500 and for that 1.0 grams of sodium fluoride per one whole 1500 liters of water. So it's a very, very, very small amount of sodium fluoride that they put into our water supply. All right. So hopefully that wasn't too bad. That is kind of a challenge problem. So we're going to move on and talk about empirical formula and mass percent composition. We're going to use it now to find empirical formula. So this is really the good, use of these things. How do we even find out what chemical formulas are? Like, how do we know water is H2O? How do we know rust is iron 3 oxide? Well, because we do this. So we take a sample of something and we break it apart into its elements, and we get a machine called a mass spectrometer, an instrument called a mass spectrometer, will give us a printout of here's the percent composition of all these elements in your compound, and then you can either put this into a computer to run some math, or you can run some math yourself and you can figure out the formula of that compound. So we're going to talk about empirical formula. So let's just quickly, before we jump in, define what that means. An empirical formula is the lowest whole number ratio formula. Okay. So I want you to think about what type of compound always is the lowest whole number ratio. And is there a type of compound that might not be lowest whole number ratio? So that's the type of compound that maybe is going to be more interesting for us to look at. So an empirical formula is just the lowest whole number ratio formula that you can get of a compound. And it's real life. It's like, hey, I find this much of this thing and this much of this thing, and I weighed it, and what's the formula? So let's say that we decompose a sample of water in the lab. We find that it produces 3 grams of hydrogen and 24 grams of oxygen. So let's work this out. So I'm going to follow, actually, these steps. So it may be helpful for you to screenshot these steps here so that you can use them, or pause and just write them down in your notes. But these are the steps outlined in your text that will produce for you an empirical formula. So I'm going to follow these steps to solve this problem and show you how we can do so. So following these steps, I'm going to go back and forth between the steps and the problem. And let's move the steps into here. Okay, there we go. So now we can see them. First, write down or calculate as given the masses of each element present in the sample of the compound. If you're given mass percent, if we assume 100, just like I was saying before, we can just use that percent as the mass. But we're actually given masses here. So we know for step 1, we have 3 grams of hydrogen. I'm not going to say H2. I know it is H2, but we're talking simply about the element, not the molecule. We're just breaking it into elemental pieces here. And 24 grams of oxygen, just O. I know that may seem a little weird to you if you're, good on your diatomics, but that's how we're going to break it down, just elementally here, not molecularly. So number 2 is convert each of the masses to moles. So in our second step, we're going to take each of our masses and we're going to convert it to moles. Now we're using the molar mass of only the single atoms here, not the diatomic. Oops. Hopefully if I were in a real class, y'all would be yelling at me about that. Grams of hydrogen is equal to 1 mole of hydrogen. And again, you may be using a periodic table that has a few more numbers than that, but this is what I have memorized from my years of work. So you'll see that now we're using these things, these molar masses, in a very practical way. So what I like to do at this point is really not round. If you round, you're not going to get a clean answer. So I actually don't ever round when I'm doing this step because I really want good clean ratios in the end, and you'll see what I mean. Okay, so I'm not rounding at all. That's just what my calculator was giving me. All right, so I found moles. Okay, that's step 2. Step 3 says write down a pseudo formula for the compound using moles of each element as subscripts. So usually when we're talking about subscripts, we're talking about whole numbers, but your textbook is guiding you to do this whole pseudo thing. I don't always do this, but just to show you what that looks like, I'm going to write this whole number down, and I don't like this because it makes me nervous. I'm going to write something down wrong. Okay, so I can't leave it like this, right? I can't say 2.97 hydrogens for every 1.5 oxygens. Can't leave it like that. So step 4 is divide all the subscripts with the smallest subscript. This is the step people forget the most. Whoa, the step people forget the most often. So really try to remember that step 4 is probably the most important step because it is going to help you get whole numbers as fast as you can. We cannot round this. You cannot say 2.97 is 3 and 1.5 is 2 because what would you get? H3O2? You know that's not water. So we know we can't do that. Why can't we do that? Well, every mole is a huge number of atoms. So by rounding these moles, you're really changing the ratio of atoms in this molecule. So we really have to get it almost perfectly whole numbers before we can do any rounding. Now, could we round this 2.97 to 3? Sure, but we can't round the 1.5 to 2. So 2.97 to 3, that's fine. Let me go back and maybe not be so extreme. That's definitely not fine. This is okay, but because this one is not fine, I have to do something to one of these numbers. I have to do it to both. So what we're going to do in our next step is divide both of them by the smallest. So if I have 2.97029703 mole of H, and I have 1.5 mole of O, which one is smaller? The 1.5, right? So we divide both of these by the smaller, and something divided by itself is 1. This is why we do this, because it automatically is going to give us a whole number, we know for sure. And we just really, really, really hope that the other number is going to give us a whole number as well, or close to a whole number. And would you look at that? You get 1.98019802. And the rule is you can round anything that is 0.1 off from a whole number. So I can round 1.9 and I can round 1.1, but I can't round 1.8 and I can't round 1.2. So be very careful with that. So this is okay. I'll get the green light to round this to 2. So I have 2 mole of H, 1 mole of O, and we get our familiar H2O. These numbers become the subscripts of our formula. This is your empirical formula of water. And I want you just to take a look really quick at this last step. We didn't do this last step. I'm going to talk about it though. What happens if our last step didn't give us a nice 2-to-1 ratio? It gave us another 1.5 to something ratio. If the subscripts are not whole numbers, multiply all of them by some small whole number to arrive at a whole number. So what we're going to do if we don't get a nice whole number ratio here, something we feel okay to round, if we get like 1.75 here or something, we can't round that. So we have to find another number to multiply both of our numbers by to get a whole number. So what I like to do is just try some numbers. Multiply by 2, see what it gets. Multiply by 3, see what it gets. But there is a chart in your text that tells you if this is the fractional subscript you get, here multiply by this number to get a whole number. I don't like to memorize stuff. I know like, okay, a quarter is 0.25, so if I multiply by 4, I'm going to get a whole number. 0.33, 0.5, those are pretty easy. But some of the other ones, like, just try some numbers. You won't probably have to go above 5. So I also will just round 0.1 down. It's fine to do that. So let's do another practice. What's the empirical formula if you have these substances? And then I want you to also and name the metal oxide. Let's practice some naming. So hopefully you've paused and you have worked this out. And we're just going to go through step by step again. Okay, first step, let's write out all of our titanium. Reacts with oxygen so that I have 5.40 grams of the metal oxide. Okay, so we can find a percent composition here of titanium, but that's not really going to help us because what do I need to do empirical formula? I need each individual element. I have 2 elements here, titanium and oxygen. So if this is the amount of oxide, how much oxygen did I put in? Well, the amount of oxygen is going to be subtracting. If this is the amount of titanium plus oxygen minus the amount of titanium, well, if I subtract those, then I get the amount of oxygen. That's why this is more of a challenge problem, because you really have to read into what you are doing. So now I really have what I need for my starting amounts, which is my 2 elements. I can't do anything without 5.40. Could I find a percent composition and go from there? Absolutely, you can. But if you want help with that, or that's the way you went, you want me to check it to make sure it's right, you'll get the same answer at the end. You can also text me. Okay, so now we have to turn these into moles. If you're ever not sure what to do, just find moles. When in doubt, mole it out. And we're going to use our trusty periodic table to find these numbers. Now I need to go and grab the titanium because I do not have that one memorized. All right, so got that one. Let's do our conversions. And remember, we are not going to round at all. We're going to be deathly afraid of rounding when we're doing empirical formula math because we want to get those really good whole number ratios if we can. So every little number counts, especially when when we realize that we are talking about moles here, which is a ton of little particles. So rounding makes actually a much bigger difference than we might think. Okay, so I have these. What's my next step? We can write that whole pseudo formula, but I say, you know what, just skip to the next one. What's the step after the pseudo formula? The next step is to divide both by the smallest. Do not forget that step. Since the moles of titanium is smaller, I will divide both of them by that number. I know I'm going to get 1 here. And you see what I mean? The pseudo formula is totally fine to do, but I think it's just a little extra step that's not needed. I can move on to the next step and understand what I'm doing here. Ooh, look at that beautiful 1.99. We can round that to 2. So what do we get? We get a 1 for titanium, so that means that we're going to have Ti with a 1, and we get a 2 for oxygen. TiO2 is going to be, those are going to be my subscripts. So now I want you to name it. Did you name it? Did you pause? Did you try it? What'd you get? The name of this is titanium 4 oxide. Don't be confused by that crisscross. The charge of oxide is -2. Or I guess it could be titanium 2 peroxide, but we don't usually use peroxides very often, so always assume oxide unless you're specifically told to use peroxide. Okay. Fantastic. Last piece. Okay. Empirical formula is our lowest whole number ratio. But like, what about hydrogen peroxide, H2O2? That's not lowest whole number ratio. That is called a molecular formula. A molecular formula is the actual number of atoms per molecule. And sometimes they're the same. So for example, water is H2O. The molecular formula of water and the empirical formula of water is the same. But for hydrogen peroxide, we know hydrogen peroxide is H2O2. That's the molecular, that's really what that molecule looks like. But what's the empirical formula for that is just HO. So if we were to go and do all our math to find empirical formula for hydrogen peroxide, we would find HO. But that's not really the way that molecule looks. How do we know? We know because we can find the molar mass. This is always of the molecular formula. So if I run some more tests and I find the molar mass of hydrogen peroxide is twice the mass of the empirical mass, then I can multiply the empirical formula by 2. So we're looking for a factor where we can take our empirical formula mass times some factor to get molar mass, because empirical is the lowest whole number ratio. So jot these down in your notes, and then I'm running really long in this video, so we need to get to some quick practice, and then I'm done. All right, so looking at this, put this page in the wrong place. Find the molecular formula for fructose, okay? So let's say we did all our math and found our empirical formula. And I give you the molar mass of fructose, okay? And we know it's probably not CH2O because I can already see you got a lot of carbons hanging out in the structure here. It's kind of a bigger molecule. So first we have to find this factor. What's the factor difference between empirical and molar mass? So just as a quick reminder, coming from this slide, molar mass is equal to empirical mass times N. So if we're looking for N, we have our molar mass, that's of our molecular formula, over our empirical mass, which is of our empirical formula. It's not times 100, it's not a percent, but that is your N. That's a factor of difference between your two formulas. So what is our molar mass? Well, they told us it's 180.2 grams per mole. And how do I find empirical mass? Well, here's your empirical formula. We have 1 carbon, 2 oxygens, and 2 hydrogens and 1 oxygen. So we just add that up. And we get 30.03 grams per mole. And then hopefully this gives us a nice whole number factor to multiply by. And we do get 6.000, which is, we're just going to say 6. So our N here is 6, which means we're going to take our empirical formula and we're going to multiply all our subscripts by 6 times 6. equals our molecular formula subscripts. So you often see your instructors will kind of do like this. We'll do CH2O and we'll multiply it by 6. And we'll get C6H12O6. And that is your molecular formula. And that is how we find formulas from real life samples of stuff.